An aquifer is an underground layer of water-bearing permeable rock fractures or unconsolidated materials from which groundwater can be extracted using a water well. The study of water flow in aquifers and the characterization of aquifers is called hydrogeology. Related terms include aquitard, which is a bed of low permeability along an aquifer, and aquiclude, which is a solid, impermeable area underlying or overlying an aquifer. If the impermeable area overlies the aquifer, pressure could cause it to become a confined aquifer. Depth aquifers may occur at various depths. Those closer to the surface are not only more likely to be used for water supply and irrigation, but are also more likely to be topped up by the local rainfall. Many desert areas have limestone hills and mountains within them or close to them that can be exploited as groundwater resources. Part of the Atlas Mountains in North Africa, the Lebanon and Anti-Lebanon ranges between Syria and Lebanon, the Jebel Agna in Oman, parts of the Sierra Nevada and neighboring ranges in the United States' southwest, have shallow aquifers that are exploited for the water. Overexploitation can lead to the exceeding of the practical sustained yield, i.e., more water is taken out than can be replenished. Along the coastlines of certain countries, such as Libya and Israel, increased water usage associated with population growth has caused a lowering of the water table and the subsequent contamination of the groundwater with salt water from the sea. The beach provides a model to help visualize an aquifer. If a hole is dug into the sand, very wet or saturated sand will be located at a shallow depth. This hole is a crude well. The wet sand represents an aquifer, and the level to which the water rises in this hole represents the water table. In 2013, large freshwater aquifers were discovered under continental shelves off Australia, China, North America and South Africa. They contain an estimated 500,000 cubic kilometers of low salinity water that could be economically processed into potable water. The reserves formed when ocean levels were lower and rainwater made its way into the ground in land areas that were not submerged until the Ice Age ended 20,000 years ago. The volume is estimated to be 100x the amount of water extracted from other aquifers since 1900. Classification. The above diagram indicates typical flow directions in a cross-sectional view of a simple confined or unconfined aquifer system. The system shows two aquifers with one aquitard between them, surrounded by the bedrock aquiclude, which is in contact with a gaining stream. The water table and unsaturated zone are also illustrated. An aquitard is a zone within the earth that restricts the flow of groundwater from one aquifer to another. An aquitard can sometimes, if completely impermeable, be called an aquiclude or aquafuge. Aquitards are composed of layers of either clay or non-porous rock with low hydraulic conductivity. Saturated versus unsaturated groundwater can be found at nearly every point in the Earth's shallow subsurface to some degree. Although aquifers do not necessarily contain fresh water, the Earth's crust can be divided into two regions: the saturated zone or phreatic zone, where all available spaces are filled with water, and the unsaturated zone, where there are still pockets of air that contain some water, but can be filled with more water. Saturated means the pressure head of the water is greater than atmospheric pressure. The definition of the water table is the surface where the pressure head is equal to atmospheric pressure. Unsaturated conditions occur above the water table where the pressure head is negative and the water that incompletely fills the pores of the aquifer material is under suction. The water content in the unsaturated zone is held in place by surface adhesive forces and it rises above the water table by capillary action too. saturate a small zone above the phreatic surface at less than atmospheric pressure. This is termed tension saturation and is not the same as saturation on a water content basis. Water content in a capillary fringe decreases with increasing distance from the phreatic surface. The capillary head depends on soil pore size. In sandy soils with larger pores, the head will be less than in clay soils with very small pores. The normal capillary rise in a clay soil is less than 1.80 meters but can range between 0.3 and 10 meters. The capillary rise of water in a small diameter tube involves the same physical process. The water table is the level to which water will rise in a large diameter pipe that goes down into the aquifer and is open to the atmosphere. Aquifers versus aquitards. Aquifers are typically saturated regions of the subsurface that produce an economically feasible quantity of water to a well or spring. An aquitard is a zone within the earth that restricts the flow of groundwater from one aquifer to another. A completely impermeable aquitard is called an aquiclude or aquifuge. Aquitards comprise layers of either clay or non-porous rock with low hydraulic conductivity. In mountainous areas, the main aquifers are typically unconsolidated alluvium, composed of mostly horizontal layers of materials deposited by water processes, which in cross-section appear to be layers of alternating coarse and fine materials. Coarse materials, because of the high energy needed to move them, tend to be found nearer the source, whereas the fine-grained material will make it farther from the source. Since there are less fine-grained deposits near the source, this is a place where aquifers are often unconfined, or in hydraulic communication with the land surface. Confined versus unconfined. There are two end members in the spectrum of types of aquifers: confined and unconfined. Unconfined aquifers are sometimes also called water table or phreatic aquifers because their upper boundary is the water table or phreatic surface. Typically the shallowest aquifer at a given location is unconfined, meaning it does not have a confining layer between it and the surface. The term perched refers to groundwater accumulating above a low permeability unit or strata, such as a clay layer. This term is generally used to refer to a small local area of groundwater that occurs at an elevation higher than a regionally extensive aquifer. The difference between perched and unconfined aquifers is the size. Confined aquifers are aquifers that are overlain by a confining layer, are often made up of clay. The confining layer might offer some protection from surface contamination. If the distinction between confined and unconfined is not clear geologically, the value of storativity returned from an aquifer test can be used to determine it. Confined aquifers have very low storativity values, which means that the aquifer is storing water using the mechanisms of aquifer matrix expansion and the compressibility of water, which typically are both quite small quantities. Unconfined aquifers have storativities greater than 0.01. They release water from storage by the mechanism of actually draining the pores of the aquifer, releasing relatively large amounts of water. Isotropic versus anisotropic. In isotropic aquifers or aquifer layers, the hydraulic conductivity is equal for flow in all directions, while in anisotropic conditions it differs, notably in horizontal and vertical sense. Semi-confined aquifers with one or more aquitards work as an anisotropic system, even when the separate layers are isotropic, because the compound KH and KV values are different. When calculating flow to drains or flow to wells in an aquifer, the anisotropy is to be taken into account lest the resulting design of the drainage system may be faulty. Groundwater in rock formations. Groundwater may exist in underground rivers. This may occur in eroded limestone areas known as karst topography, which make up only a small percentage of Earth's area. More usual is that the pore spaces of rocks in the subsurface are simply saturated with water, like a kitchen sponge, which can be pumped out for agricultural, industrial, or municipal uses. If a rock unit of low porosity is highly fractured, it can also make a good aquifer, provided the rock has a hydraulic conductivity sufficient to facilitate movement of water. Porosity is important, but alone, it does not determine a rock's ability to act as an aquifer. Areas of the Deccan Traps in west-central India are good examples of rock formations with high porosity but low permeability, which makes them poor aquifers. Similarly, the microporous chalk of southeast England, although having a reasonably high porosity, has a low grain-to-grain permeability, with its good water-yielding characteristics mostly due to microfracturing and fissuring. Human dependence on groundwater. Most land areas on Earth have some form of aquifer underlying them, sometimes at significant depths. In some cases, these aquifers are rapidly being depleted by the human population. Freshwater aquifers, especially those with limited recharge by snow or rain, also known as meteoric water, can be overexploited and, depending on the local hydrogeology, may draw in non-potable water. A saltwater intrusion from hydraulically connected aquifers or surface water bodies. This can be a serious problem, especially in coastal areas and other areas where aquifer pumping is excessive. In some areas, the groundwater can become contaminated by arsenic and other mineral poisons. Aquifers are critically important in human habitation and agriculture. Deep aquifers in arid areas have long been water sources for irrigation. Many villages and even large cities draw the water supply from wells in aquifers. Municipal irrigation and industrial water supplies are provided through large wells. Multiple wells for one water supply source are termed well fields, which may withdraw water from confined or unconfined aquifers. Using groundwater from deep, confined aquifers provides more protection from surface water contamination. Some wells, termed collector wells, are specifically designed to induce infiltration of surface water. Aquifers that provide sustainable fresh groundwater to urban areas and for agricultural irrigation are typically close to the ground surface and have some recharge by fresh water. This recharge is typically from rivers or meteoric water that percolates into the aquifer through overlying unsaturated materials. Occasionally, sedimentary or fossil aquifers are used to provide irrigation and drinking water to urban areas. In Libya, for example, Muammar Gaddafi's Great Man-Made River project has pumped large amounts of groundwater from aquifers beneath the Sahara to populous areas near the coast. Though this has saved Libya money over the alternative, desalination, the aquifers are likely to run dry in 60 to 100 years. Aquifer depletion has been cited as one of the causes of the food price rises of 2011. Subsidence. In unconsolidated aquifers, groundwater is produced from pore spaces between particles of gravel, sand, and silt. If the aquifer is confined by low permeability layers, the reduced water pressure in the sand and gravel causes slow drainage of water from the adjoining confining layers. If these confining layers are composed of compressible silt or clay, the loss of water to the aquifer reduces the water pressure in the confining layer, causing it to compress from the weight of overlying geologic materials. In severe cases, this compression can be observed on the ground surface as subsidence. Unfortunately, much of the subsidence from groundwater extraction is permanent. Thus, the subsidence is not only permanent but the compressed aquifer has a permanently reduced capacity to hold water. Saltwater intrusion. Aquifers near the coast have a lens of freshwater near the surface and denser seawater under freshwater. Seawater penetrates the aquifer, diffusing in from the ocean, and is denser than freshwater. For porous aquifers near the coast, the thickness of freshwater atop saltwater is about 40 feet for every 1 foot of freshwater head above sea level. This relationship is called the Gibbon-Hertzberger equation. If too much groundwater is pumped near the coast, saltwater may intrude into freshwater aquifers, causing contamination of potable freshwater supplies. Many coastal aquifers, such as the Biscayne Aquifer near Miami and the New Jersey Coastal Plain Aquifer, have problems with saltwater intrusion as a result of overpumping and sea level rise. Salination. Aquifers in surface-irrigated areas in semi-arid zones with reuse of the unavoidable irrigation water losses percolating down into the underground by supplemental irrigation from wells run the risk of salination. Surface irrigation water normally contains salts in the order of 0.5 grams per more, and the annual irrigation requirement is in the order of 10,000 m³ per more, so the annual import of salt is in the order of 5,000 kilograms per more. Under the influence of continuous evaporation, the salt concentration of the aquifer water may increase continually and eventually cause an environmental problem. For salinity control in such a case, annually an amount of drainage water is to be discharged from the aquifer by means of a subsurface drainage system and disposed of through a safe outlet. The drainage system may be horizontal or vertical. To estimate the drainage requirement, the use of a groundwater model with an agro-hydrosalinity component may be instrumental, e.g. SOHISMOD. Examples: the Great Artesian Basin situated in Australia is arguably the largest groundwater aquifer in the world. It plays a large part in water supplies for Queensland and remote parts of South Australia. The Guarana Aquifer, located beneath the surface of Argentina, Brazil, Paraguay, and Uruguay, is one of the world's largest aquifer systems and is an important source of fresh water. Named after the Guarani people, it covers 1,200,000 square kilometers, with a volume of about 40,000 cubic kilometers, a thickness of between 50 meters and 800 meters, and a maximum depth of about 1,800 meters. Aquifer depletion is a problem in some areas, and is especially critical in northern Africa. See the Great Man-Made River Project of Libya for an example. However, new methods of groundwater management such as artificial recharge and injection of surface waters during seasonal wet periods has extended the life of many freshwater aquifers, especially in the United States. The Ogallala Aquifer of the central United States is one of the world's great aquifers, but in places it is being rapidly depleted by growing municipal use and continuing agricultural use. This huge aquifer, which underlies portions of 8 states, contains primarily fossil water from the time of the last glaciation. Annual recharge in the more arid parts of the aquifer is estimated to total only about 10% of annual withdrawals, according to a 2013 report by research hydrologist Leonard F. Konikow at the United States Geological Survey. The depletion between 2001 to 2008, inclusive, is about 32% of the cumulative depletion during the entire 20th century. Quote, in the United States, the biggest users of water from aquifers include agricultural irrigation and oil and coal extraction. Cumulative total groundwater depletion in the United States accelerated in the late 1940s and continued at an almost steady linear rate through the end of the century. In addition to widely recognized environmental consequences, groundwater depletion also adversely impacts the long-term long-term sustainability of groundwater supplies to help meet the nation's water needs. An example of a significant and sustainable carbonate aquifer is the Edwards Aquifer in central Texas. This carbonate aquifer has historically been providing high-quality water for nearly 2 million people, and even today is full because of tremendous recharge from a number of area streams, rivers and lakes. The primary risk to this resource is human development over the recharge areas. Discontinuous sand bodies at the base of the McMurray Formation in the Athabasca oil sands region of northeastern Alberta, Canada, are commonly referred to as the Basal water sand aquifers. Saturated with water, they are confined beneath impermeable bitumen-saturated sands that are exploited to recover bitumen for synthetic crude oil production. Where they are deep-lying and recharge occurs from underlying Devonian formations, they are saline, and where they are shallow and recharged by meteoric water, they are non-saline. The BWS typically pose problems for the recovery of bitumen, whether by open-pit mining or by in-situ methods such as steam-assisted gravity drainage, and in some areas they are targets for wastewater injection.